Well, good afternoon. Welcome to our introduction to Chapter 9. Let me write that up there. I was going to say we do, so we don't get lost, but it's really so I don't get lost. Chapter 9. And in this chapter, we're going to be introduced to centroids. At its most basic level, centroids are not new to us. We know a little bit about them. We've called them something different in previous chapters. So previously, we've seen this center of gravity. We've worked with some diagrams that had the initials C dot G dot. So that was the abbreviation of center of gravity. And center of gravity is the point where the weight of the object acts on, right? There's a problem in the book. I don't remember if we did it or not, but it's a car. I call it a car problem, mainly because it's a car. Steering wheel. Doors. Cool looking tires and wheels. Nice looking hubcaps. And in that drawing, it'll get something like the center of gravity. Maybe it's right here. And it'll say CG. And it'll say something like the mass of the car, the mass of the car is 3,000 mass of car is 3,000 pounds, right? So when we drew our free body diagram, we drew that like that, 3,000 pounds. And there was other things, right? We knew that the distance from the front to that center of gravity point to the back, maybe that was 5 feet, and maybe this was 4 feet. I don't know. I'm not an expert on cars, but anyway, so center of gravity. So in this chapter, we're introduced to the term centroid. Centroid, and it's weird. If you're looking at the textbook on page 180, if you're not, that's okay. My favorite definition of centroid is written on page 180 in the chapter objectives. And the first chapter objectives locate the centroid, and it says it's the geometric center. Geometric center. So that's what we're going to be looking for in this over the next week and a half, maybe 2 weeks. We're going to be looking at, given an object, we're going to calculate its geometric center. And there's really 2 ways to do that, right? So there's 2 methods. The first method is by inspection. So for some objects, by inspection, for some objects, we can just look at it and figure it out. Pretty easy to do. Maybe an example would be, maybe this, right? I mean, where do you think the geometric center of this rectangle is? Right. So, I mean, if you knew that the rectangle, this was oops, we don't want that, do we? If we knew that this rectangle, we don't, man, I don't even know I have, there we go. Sorry about that. If we knew this rectangle was like 4 inches that way and 2 inches tall, and I asked you where the geometric center was, and you knew it was a homogeneous object, right? So the same material throughout, same thickness throughout, you would say, well, that's easy, Rick. It's clearly exactly right here, 2 inches from, it's 2 inches this way, which happens to be 2 inches this way, and it's 1 inch this way, which happens to be 1 inch this way, right? Geometric center, right? Geometric center. We could do lots of them. We do lots of them. Ovals, right? Ovals have a geometric center, can be found by inspection as long as it's a homogeneous, right? We're talking, so unless we're told otherwise, we will assume that the object is homogeneous. Same thickness, same material, weight or the mass is equally distributed, all right? So if I gave you an oval and told you, hey, look at my oval. My oval is 7 foot tall and it is 3 foot wide at its widest diameter. Hey, what do you think the center or the centroid of my oval is? Someone would say, well, Rick, it's perfectly symmetrical. I mean, it's perfectly symmetrical, so it's got to be in the exact center of the line of symmetry, right? So it'd be 3.5 foot top to bottom. Or if it's 7 foot from top to bottom, 3.5 foot center, and it would be if it's 3 foot across at its widest, and again we're talking about symmetry here, then it's 1.5 foot in, right? The centroid. And you'll have the opportunity to practice that. I mean, just a couple things. We're looking at the symmetric axis or the axes of symmetry when we look at these things. Let me kind of draw them up here. Do the best I can anyway. The axis of symmetry. This has an axis of symmetry. I have to move that one. Axis of symmetry. While I'm here, let's talk about it. This is the x-axis of symmetry. This is the y-axis of symmetry. X-axis of symmetry, y-axis of symmetry. You probably already knew that. But for the folks that are taking notes, might be important. Okay. All right. So let me pause, erase, and get ready for the second the second method. So that is looking at an object and saying, hey, the axis symmetry, I can find the centroid by inspection. I can find it by inspection because it's a symmetrical object, and piece of cake. And you'll have opportunity to look at some homework questions that deal with the axis of symmetry, and you kind of play around with that. So let me pause and so we can talk about the second method. I'll be right back. All right, welcome back. It took me a couple minutes to get the drawing going, so we're going to look at a problem to kind of talk about the calculations. So locate the centroid of the plane that's shown. It is not symmetrical. Okay, so this is, if you remember in algebra, there was a type of problem in algebra. I called it the deck problem. And so in algebra, it would look something like this. You're building a deck. I don't know if this is in the algebra books now, but you're building a deck. You are looking to put a hot tub in the deck. A typical problem was something like you had to find the area of the shaded area, right? It's essentially you're looking for the area of the deck after you cut out the hole for the hot tub. Or another deck problem would have been something like you're building a deck. It looks like this. and they want to know the area of the whole thing. So in both of these problems, you do it by pieces, right? I mean, in the hot tub problem, you take the area of the big rectangle and subtract their area for the hot tub, right? Because you're cutting that wood out and the hot tub's going to sit in there. In the second deck with the two rectangles and the quarter circle, you would find the area of each of the rectangles, add them together, add that to the area of the quarter center, and you would have the total area. That's kind of the technique we're going to be looking at in the calculations we're about to do. We're going to take a figure, a composite figure, a figure that's made up of more than one shape. We'll find the centroid for each of those shapes and add them together, okay? There's a couple things that we need, right? So on textbook page 454, table A1. You need that out. So kind of like page 82 where I said, hey, this is a page where you want to put a bookmarker in or you'll stick or something so you can refer back to it quickly. Same thing with page 454. We're going to be using it quite a bit over the next week and a half, 2 weeks or something like that. So, so we need that. Okay, so grab that out real quick. Pause the video while you do that, then unpause. All right, welcome back. If you've taken a look at page 454, you'll see a couple things. There's some common shapes there. We'll look at those. There's also 3 columns on the right-hand side. All right, so those 3 columns are areas. So that is the area of the shape. So that gives you the formula for finding the area of that particular shape, whatever shape it is that we're going to be dealing with. There is another column. It's the X with the bar over it. That is a distance. Okay, that is the distance. And it is the distance from where the X and Y axis intersect. Let me write that up here. XY is the distance horizontal distance from the intersection of the X and Y axis. We know the intersection of the X and Y axis is the origin. I guess I could have wrote that. Y bar is the distance. This time's vertical distance. Vertical from the intersection of the X and Y axis. Okay, so one of the things that you need to note as soon as you see a problem is you need to quickly identify the X and the Y axis. So in the problem that we're going to work here in a second, the X and Y axis are I've got them identified, right? You see the X and the Y. So those are the X and Y axis. Okay, so that's important. Let me kind of need to erase that red stuff because we are definitely going to need the room. I say definitely like it's not really that difficult and not complicated. Just takes a little practice. So there's 3 things that we need. Okay, there's 3 things that we're going to be there's maybe it's 7 things. Let me get a table. Okay, so for each shape, we're going to calculate the area of the shape. Okay, for each shape, we're going to measure the distance, the horizontal distance from the origin to the X part of the centroid of the object. Okay. For each shape, we're going to calculate y bar. That's the y distance from the origin in the y portion of the centroid for that. Then it's multiplication. It's x bar times the area, and it's y bar times the area. We'll get that part done, and then we'll grab the last couple of calculations. Okay, now it is a composite shape, so I'm going to break it into two shapes, right? So there's no, I'm looking at the formulas on page 454. There's no area formula for this this L thing we've got going on here. So I'm going to break it into two shapes. Okay. Sometimes it might be 3 shapes, 4 shapes, whatever. But we want to break it into shapes that are known, shapes we can find the area of. I'm going to use pink because it stands out. So I'm going to look at these two shapes here. Shape 1 is the smaller of the two rectangles. Shape 2 is the larger of the two rectangles. Okay. Shape 1 is the smaller of the rectangles. I've cut it to make it smaller. Shape 2 is the tall rectangle. Now, the question is, so I'm about to erase the pink stuff to show you then something, then we'll come back to it. And the question is, well, Rick, why'd you do it like that? I mean, could you have done it this way? Could you cut it into these two shapes? And the answer is you absolutely could cut it into those two shapes. I just chose to do it the other way. So let me go back to that. And the only reason I chose to do it that way is because that's how I worked it out. So, okay. All right. The first thing we want to do is find the area of rectangle number 1. So, all right, and I'm going to call it right here as area of shape number 1. So the area of a rectangle, remember, is length times width, right? All right, so you don't get sucked in. The length of the rectangle, the shape 1 is what I'm going to call it. The length of shape 1 is not 240. The length of shape 1 is 240 millimeters minus 30 millimeters, which is 210 millimeters, right? It's this 240 minus this 30 that's no longer a part of that rectangle, okay? So 210. And then the width of shape 1, the width of shape 1 is 30 millimeters, right? So the area of shape 1, 210 millimeters times 30 millimeters, which is 6,300 millimeters squared. Okay. All right. Next thing. Next thing is to find x bar. So I'm looking at the formula of a rectangle. To find x bar, we are going to find the middle. How far is it from? So we're looking for how far is it? Where am I at? How far is it? How far is it from the origin to the middle, or the horizontal middle of that rectangle, shape 1? So if the rectangle is 210 millimeters long, the horizontal middle of that is 105 millimeters. 210 divided by 2. Okay. All right. Y bar. Looking at the table to find y bar, it's the height of the rectangle divided by 2. So the horizontal distance, halfway, so looking from the origin to the top of our object is 30 millimeters. 30 divided by 2 is 15. Okay, that's pretty easy. Doing the arithmetic, let me get my calculator out. So 6,300. So our third column is x bar times area. So 6,300 times 105. We get 661,500. 661,500. And that'd be millimeters to the third power, right? Millimeters squared times millimeters. And then the y bar times area is 94500 millimeters cubed. Okay. All right. Area 2. Area 2. All right, area 2, same idea. The area for shape 2 is length times width. The length is 30. 30 millimeters. And the height or the width is 300 millimeters. Huh. So 30 millimeters times, I'll point it out once I get this written down. I think that's 9,000 square millimeters. So 30 millimeters times 300 millimeters. Okay, so far so good. All right. Okay, we're looking for X bar for the second object. X bar, remember, is measured from the origin. Measured from the origin. So 1/2 of 30 is 15 millimeters. That is not X bar. How far do you have to travel from the origin to get to that that middle, if you will? All right, so it's 210 to get to the object, and then it's 15 millimeters to get to the middle distance. The middle distance. Okay, so X bar for this one is the 210 millimeters it takes to get to our object from the origin, plus the 15 millimeters that is the middle distance of that 30. So X bar for this one is 225 millimeters. So how far do you go from the origin to get to that point? So looking only at object 2, the formula says, hey, it's the base of the object divided by 2. Right? So the base is 30. 30 divided by 2 is 15. But to get there from the origin, I have to travel 210 millimeters and then 15 more. All right, Y bar. Y bar is horizontal vertical distance from the x-axis up to the middle. So starting at the x-axis, so that object is 300 millimeters tall. So half of that, according to our formula, we're to take the height divided by 2. Half of 300 millimeters is 150 millimeters. Again, we do the arithmetic or do the multiplication. 9,000 times 225, 202, 5,000. X bar is 202, 5,000 cubic millimeters. And then the next one is 9,000 times 150. 135 and then zeros. 135, 1, 2, 3, 4 zeros, cubic meters, or cubic millimeters. Okay. All right. Only a couple more pieces to go. All right. We need to add this column here, and this column here. Okay. So we need to add the area column, the X bar area column, and the Y bar area column. 6,300 plus 9,000 is 1,500. 1.300 square meters. Uh, 661,500 plus 202,512, 3 zeros. 2,686,500. 2,686,500 cubic millimeters. And the last column, 94500 plus 135, 4 zeros, 1444,511. 1444,511 cubic millimeter. Okay. Capital X bar is equal to the summation of X bar A divided by summation of the area. In our case, that's 2,686,500 cubic millimeters divided by 15300 square millimeters. And I think you get something like 175.6 millimeters, right? You got cubic millimeters on the top, square millimeters on the bottom. The squares would cancel out, leaving us just millimeters, and I think that's the arithmetic is correct. Do the same thing, gigantic, or the capital Y bar, summation of the Y bar A's divided by a summation of areas. That's 144,511 cubic millimeters. 15300 square millimeters. And I think that's something like 94.4 millimeters. That's what I'm going to call it anyway. All right, so what does it mean? What does it mean? So the capital X bar and the capital Y bar describe the actual location of the centroid of the object that we just looked at. Okay. So it says the actual centroid for the location of this object is at 175.6 millimeters. So that's from 0. Happens to be exactly like right around in here. And then 94 millimeters, probably right in here. The centroid of this object, 175.6 millimeters from the origin in the x direction, 94.4 millimeters from the origin in the y direction. There is the centroid of our object. I noticed something weird. I don't know if you noticed it or not. Let me label it real quick. The centroid. The centroid. The centroid's not on the object. The centroid of this plane is not on the object. And that's okay. It's okay. It doesn't have to be on the object. It has to do with the geometric fixtures and the math that's involved. Your author and the textbook takes a couple pages to explain it. I'm okay with it not being on the object. I want to add a couple notes up here for the folks that are trying to get the steps down. What colors do we have left? All right, we're going to use orange, even though I don't like it. Okay. Okay. Step 1. Identify the x and the y-axis. Identify the X and the Y axis. Sometimes it's given, sometimes you can pick. Okay? Sometimes it's given, sometimes you can pick. Step 2. Break into shapes. Break into known shapes. Step 3. Calculate the area. Step 4. Find lowercase x bar and lowercase y bar. So lowercase x bar, remember, we use the formula that's given in the table. We'll do a couple more practice problems to get some more practice at it, but we use the formula that's given in the table. That's the horizontal distance from the origin for the shape that we're working on. Y bar is the vertical distance from the origin for the shape that we're working on. Step 5 is a multiplication step. Step 6, calculate the summation of the area. In other words, add all the areas together. Step 7, calculate the summation of x bar A and y bar A. I'm going to write the 7 over in the middle. And then step 8 is calculate capital X bar and capital Y bar, which is the location of the centroid of the composite figure. And then finally, step 9, plot capital X bar, capital Y bar, also known as the centroid, on the figure. Okay, I'll put it right over here. 9, plot gigantic X bar, gigantic Y bar on the figure. Okay. All right, so I'm going to stop the recording for this and get set up for another example. See you guys in a little bit.